Hello. Good morning, students.
Hello, good morning, sir.
I think the Boolean algebra first class is not clear because audio and video is not clear. When I have saw the recording, so no any PPT sharing. I think once again I have to repeat this first class, that is Boolean algebra. So one class I will repeat. After that, that is after logic gates. Once again, we will go to the last slides of this chapter, that is K-maps. Before K-maps, once again I will repeat this Boolean algebra, which is developed by George Boole during 1854, based on 0 and 1. So logic gates are the basic logic gates which are invented by George Boole, named AND gate, OR gate, NOT gate. They are called basic gates, and these are the fundamental logic gates. AND gate is a logic circuit which has many inputs and one output. Output is high only when all inputs are high, otherwise low. So figure shows AND gate. I think these things are not seen in the PPT of the first class. So in the recording, it is not reflected. That is why once again I am repeating. So this is a logic symbol of AND gate. Only two input AND gate it is. Two inputs and Y is output. So for such a two input AND gate, Y is the product of inputs, that is A into B. So if there are n number of inputs, Y is equal to A into B into C into up to n. So output is a product of the input variables. This is called Boolean expression. This is a logic symbol. This is the truth table. The table is the truth table, it is called. So which will explain the working of this logic gates. Inputs are A, B with the two variables A and B with the binary combination 0 and 1. So we have 0, 0, 0, 1, 1, 0, 1, 1. So for these combinations, output Y is equal to A into B, 0 into 0, 0, 0 into 1, 0, 1 into 0, 0. So 1 into 1, 1. That is, when all inputs are high, that is 1, output is 1. Otherwise, if any one of the input is 0, the 0 multiplied by anything is 0. That is why it is Y is equal to AB and is AND gate. Next is OR gate. So OR gate is a logic circuit which has many inputs and one output. So output is sum of the inputs. Output is the sum of the input variables. That is Y is equal to A plus B plus C up to n. Here the logic diagram is for only two variables, two inputs. Output is Y with the two input and output Y. So A, B are the inputs, Y is the output, Y is A plus B. So this is a logic addition. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is actually in binary addition, it is 1, 0, but in logic addition, it is 1 only. So high, output is high. So that means output of OR gate is low only when all inputs are low. If any one of the input is high, output is high. Irrespect of other 0, if any one of the input is high, output is high. This is the actual definition The OR gate is one in which output is low when any one of the input is low, otherwise it is high, and it is denoted by symbol like this. Y is equal to a plus b is the Boolean expression. Then third logic gate is NOT gate. It has only one input and one output. Output is a complement of the input, not input. A complement. If A is input, output is A complement. If B is input, output is B complement. So here output is B, input is A, Y is equal to B. B means that is Y is equal to B equal to A complement. So 0, 1, 1, 0. This is a NOT operation. It is denoted by Y is equal to A complement or not A. Not A means whatever A is there, it is not. Not means inversion. So that is called a NOT gate. So similarly, positive and negative logic in digital electronics, they are represented by waveforms. In positive logic representation, bit 1 represents high, bit 0 represents low, as in figure 2a. High is represented by plus 5 volts and low is minus 5 volts. This is one of the type of representation. So positive logic representation. Other type of representation is same positive logic representation. One is plus 5 and 0 is represented, but in the uppercase 0 is represented by minus 5. Both are correct. This is representation of positive logic. In two ways we can represent. Similarly, negative logic. In negative logic, plus 5 volts is 0 and minus 5 volts is 1. So R for 0 plus 5 and minus, that is a 0 is a logic 1. Complement, that is opposite of that. This is 0, this is 1. This is 0, this is 1. So two ways we can represent both logic high and low. In between high and low, generally there is a region called logic margin. Generally it is represented by waveform like this. Suppose this is a low, this is a low, suppose this is high. So generally from here to here, this is called a nil region, and in this region, this is below this it is 0, above this it is high. So this is called a logic margin, which separates. For example, in a PN junction diode, up to 0.7 it never conducts. Up to 0.6 voltage it is called a knee voltage. Above 0.6 it starts conducting. Exactly above 0.7 it conducts for the silicon. Similarly, for the germanium 0.2, below 0.2 it is 0, above 0.2 it is high. In this way, there is a logic margin in between which it is called forbidden, neither low nor high. Generally in between it is called forbidden gate. This is a forbidden. Above certain level, say 1.8, if it is 2 it is 1.8, if it is 4, 4.8 or 4.2, above 4.2 it is considered as high, below 4.2 it is neither low nor high. So similarly for germanium, for 0.7, above 0.7, say 0.8, it is considered as high, below 0.8, that is 0.7, it is considered as low. So but above 0.7 it is in the forbidden, not completely high. So this in between region is called logic margin. For low there is a maximum logic margin above which it enters into high level. So for high that is 4.2, above 4.2 and 5. So this is high level. Below 4.2 it is forbidden. So above 4.2 it is high level. So in between two it is neither high nor low. Such a region is called forbidden region, which is unpredictable in case of logic circuits, because either 0 or 1, only two values in between that variation, that is neither low nor high. So in few of the leakage cases the circuit never works. So that is called logic margin. So now Boolean laws, this is clear. So till this, so it is not PPT is not visible in recording. That is why I have the doubt. No audio is there, but video, that PPT is not visible clearly. So that is why once again I repeated. Now let us move to the next topic, that is last slide. K-maps. These are the things which are completed. Now let us have the introduction to Karnaugh maps. Karnaugh, Karnaugh, a name of a person, mathematician, great scientist, developed a map. Map means a diagrammatic representation to represent the Boolean expression which is in the form of truth table, in the form of either SOP or POS. Binary value for SOP is 1, binary value of POS is 0. Either 0 or 1 it is represented. That is why this map has a very important. The K-map is similar to truth table. It consists of an array of cells, rows and columns. So each cell is a bit in the binary. Cells in which each cell represents a binary value of a variable. K-map are used to simplify Boolean expressions. K-map is a diagrammatic representation of truth table. It consists of an array of cells, both in horizontal and vertical direction. So the arrays may be of 2, 3, 4, 5 variables, any number of variables. So up to 5. For your syllabus only 4, up to 4 you have to study. Up to 5 variables we can represent K-map. Above 5 variable K-map method is not suitable. So that is why it is limited up to 4 only. For 5 3-dimensional K-maps we have to use. So let us see further. So now this is used to represent the simplification of Boolean expressions. K-map can take two forms, SOP and POS, according to need of problem. A K-map table representation, but it gives more information than truth table, more informative than truth table. We fill grid of K-map with 0 and 1s, then solve it by making grouping. Some rules are there in solving, simplifying Boolean expressions. Steps to solve expression using K-map. First, select K-map according to the number of variables. Identify min terms and max terms in a given problem, like SOP and POS. For SOP, put 1 in blocks that is in cells of K map, irrespective of min term, that is zeros elsewhere. For POS, 0 in the blocks of K map, and to represent the max terms, and blanks are represented by ones, that is opposite. Make rectangular groups containing total terms in power of 2, like 2, 4, 8. So we have two group except one. If and try to cover as many elements as you can in one group. From groups made in step 5, find the product term and sum them up for SOP form. SOP form. This is called K map of 3 variables. This side A, this side B. BC combination consists of 2 variables, 0, 0, 0, 1, 1, 1, 1, 0. Why not 1, 0, 1, 1? It is not suitable. First we have to write 1, 1, then 1, 0. Here only one variable, 0 and 1. So this is the order we have to choose. 0, 0, 0, 1. Next 1, 0. Instead of 1, 0, 1, 1, 1, 0. This is the way of representation of K map. Why? Don't ask. No question for why. This is applicable when we write like this, like a gray code. So this is 0 and 1. For 3 variables, how many cells? 7, 8 cells, 0 to 7. In truth table, ABC is written as 0, 0, 0 to binary 1, 1, 1. So this is so many, 0 to 7, totally 8 combination. That is why it is 8 cells to represent the truth table in the form of K map. Here there is a 3 variable equation. Z is equal to sigma ABC. 1, 3, 6, 7. 1 means first term, it is first term. In case of this is a 0, 0, 0. 0, 0, 0 is A complement, B complement, C complement. This is the first term. Second term, 3. 3 is written as A0, B complement, sorry, this is A, complement, B, C, 0, 1, 1. 6 is 0, 1, 1, 0. 0 you leave, 1, 1, 1, 0. A, B, C complement. This is 6. Whereas 7 plus ABC. ABC. So this is in the form of binary values. 0, 0, 0 first term. No, this is 0, 0, 0. First term is 0, 0, 1. 1 is a C. This is C. This is A complement, B complement, C. This is A complement, B complement, C, because 1, 0, 0, 0, there is no term. 1 there is term, 3 there is term, 6 there is term, 7 there is term. This is the SOP Boolean expression in a min term form. Min term form means summation. A, B, C is the variable and it is represented by 1, 3, 6, 7. Four terms are there, 1, 2, 3, 4. In truth table, first term is not there, second term is there, that is 1, 0 is not there, 1 is there, 3 is there. Say that means high for these remaining all 0, 0, 0. See first term A complement, B complement, C. A complement, that is 0, B complement, C, this one 1. Here you enter 1 in the K-map. Second term is A complement, BC. A complement means 0. BC, BC, both are present. 1, 1. This is 1. So this is also 1, this is also 1. Then next term, wherever term is there, you put 1 for SOP. A, B, C complement. A is 1 here. B here. C complement here is there. The last one. A, B, C complement. 1, 1, 0. Here you put. This is 1. So next A, B, C. So A is 1, B is 1, C is 1. Here. This is 1. That means 1, 2, 3, 4 terms are there. 1, 2, 3, 4. In this way, we have to draw the K-map for the given SOP form of Boolean expression. Remaining all zeros. This is not there, this is not there, this is not there, this is not there. For 0, 0, 0, in the truth table, 0. In the output, 0. Y is 0. 0, 0, 1. 0, 0, 1. There is 1. Similarly, 1, 0. There is 1. 0, 1, 1. Third term. Second term is not there, no? Second term is not there, it is 0. 3, 1. After 1, 3. This is 1. Similarly, 6, 4, 1, 0, 0. There is 0. Note 1, not 1, 0. Whereas 1, 1, 0. There is 1. 1, 1, 1. There is 1. This is what the Boolean expression 1, 2, 3, 4. 4 terms are there. These are entered. Remaining are zeros. This is a SOP representation. So here now group. We have to group. In grouping there are certain rules. In grouping, these cells are called adjacent to each other. For this is adjacent. For this is adjacent. For this is adjacent. This is also adjacent. For this is also adjacent. This is also adjacent. For this is also adjacent. This is also adjacent. For this is adjacent. And this is adjacent. This is adjacent. So in this way, adjacency is followed in grouping. We can group a single cell. We can group 2. We can group 4. Odd is not possible except 1. 2, 4, 6, 8, like that. Up to 16. For 4 variables, all 16 we can group at a time. And this type of adjacency is called wraparound, like this. So these two and these two we can group. Upper these two, lower these two we can represent. This adjacency is called wrap around adjacency. Wrap around adjacency. Adjacency is followed in grouping. To simplify a Boolean expression by K-map method, we have to group the variables. How to group? Only ones in SOP, only ones are grouped, not zeros. Ones are grouped. So here 1 1 is there, here 1 1 is there. These two are adjacent, that is why these are grouped. This is another grouping. This is another grouping. 3 groups we can form. 1, 2, 3. This group will give you groups of 2 elements in one group. Two elements in one group. In this group, no need of this group, as we have already covered those ones. These ones are already covered. This comes in this group. This comes in this group. That is why the third group is not necessary. That is why we are leaving this. Only 2 groups. This group, this group. This group, if you take this group, here elements are, this is A, 0 0 1. This is 0 0 1. This is 0 1 1. 0 0 1, 0 1 1. 0 0 1, 0 1 1. If you group this, these are getting cancelled. Complements are getting cancelled. Only remains 0 1. 0 means A complement. This is C. So that results in A complement C. Similarly, in this group, only remains AB. In this group, A, that is 1 1 1 1, and here 1 1 0. So these are eliminated. Complements are eliminated. Remains common 1 1. 1 1 is AB. So AB remains. Therefore, simplified Boolean expression y is equal to A complement C plus AB. A complement C plus AB. This is not in standard form, but simplified. This SOP is simplified in this form. So such a large 1, 2, 3, 4 terms becomes only 2 terms. Same functions done by this Boolean expression is also done by this Boolean expression. This is what the aim of the simplification of Boolean expressions. So we stop here only because time is over. So in the next class, again we continue the K-map, how to simplify Boolean expressions using K-map. In K-map, there are 2 variable K-map, 3 variable K-map, 4 variable K-map, 5 variable K-map. This is ABCD. This is AB. Only 2 variable. AB. Only 4 cells we have. Only 4 cells we have. ABC. 1, 2, 3. So 8 cells we have. 1, 2, 3, 4, 5, 6, 7, 8. 8 cells we have. ABCD. 16 cells we have. The grouping adjacency is followed. A wraparound adjacency is followed. Maximum number of ones you group. Grouping must be done only 2. Possible grouping 2, 2 and 3 we can't group. These 3 we can't group. Only 2. Either this 2 or this 2 or this 2. So if 4 are there, 1, 1, 1, 1, all 4 we can group. Suppose here 1, 1, 1, 1, we can group this called wraparound adjacency. In simplification, we can follow the grouping. So first step, enter the given Boolean expression in the K-map. Identify the maximum cell grouping. Then group them by following the rules 1, 2, 4, 6, 8. Adjacency must be followed. Don't consider, suppose 1, 1, 1, 1 is there. So all 4 we can group. Don't consider only 2, 2. Maximum grouping first treated. Then the next lower group, lower group. First 16, then 8, then 4, then 2, then 1, last one. Suppose here is there 1. Suppose here is 1. So this can be grouped like this. This is one group. This is another group. This is another group. Not necessarily square you have to draw. You group like this. Grouping it is called. Here square is used. Let it be. So we stop here only. In the next class, again we continue. Yes, Sagar, any doubts?
No, sir.
K-map. Again we repeat in the next class. K-map is a diagrammatic
Sir.
representation of truth table. It is better than the truth table. Have advantage in simplification of Boolean expression by minimization. Okay, see you in the next class.
Viresh, hello.